Welcome everyone to Product One's technical web series. Today we're looking at one of my favorite topics of all times, which is generative design inside Creo Parametric. So now, for those of you who do not know generative design, it is basically an AI or artificial intelligence driven tool inside a Creo design environment. So basically, the tool is all about helping companies design the best products in less time, no doubt about it. So what this AI does, it automatically generates the optimum designs from a set of requirements. So those requirements or specifications, it can be specified loads, constraints, and material, including certain manufacturing processes. So let's take a simple example. What you see in front of your screen, as many of you are familiar with multi-body designs, I'm having one component that has multiple bodies. So if I take this into my generative design environment, obviously for the sake of saving time, I've already basically applied loads and constraints on this one. However, what I want to do is showcase that the first thing that I want to do is specify what I call preserved geometry. So think about it this way. Preserved geometry, it will be the geometry that the generative design will basically either bond to and essentially neglect from this particular process, apart from bonding what it is going to generate to. So the other aspect that I'm going to showcase here is what I'm going to be calling excluded geometry. So what do I mean with that? So if you can look here, I've got what you call an envelope. So this is where the geometry is more or less likely to be generated. Remember, the algorithm itself will pinpoint in terms of, okay, this is what this guy really needs. He's got these preserved geometry. Now I need to generate components to fit that. If I go into my model tree, and I just want to quickly show a couple of things here. So you can't necessarily see on the screen. However, what I can do is I can say, show me the excluded geometry. So as you can see, these are series of cuts that will be incorporated from the shape that I'm about to generate. So all that I need to do now is add what you call the design criteria. So the design criteria could be a couple of things. For an example, I can specify that I want the limit of this product to be 1.5 kilograms. Maybe I'm designing a bracket for aerospace or an aircraft for maximum strength and minimum weight, or whatever the case is, whatever the design criteria you have. Of course, you can specify a couple of constraints. So what I'm going to put here is symmetry. So all I'm saying is, whatever the system is going to do, let this generation of the geometry to be symmetrical around that data plane selected. And last but not least, I'm going to specify the material. I select the material, and that is all that I need to do to define the study. So the good thing about this is, if now I were to run this particular study, so if I were to hit optimize for an example, you will see that it will showcase here the timestamp, and it will show here at the bottom in terms of what is the system currently doing. So I'm going to pause this recording just slightly so that we speed up to the results section. It does not take long, only a couple of minutes, but I'm just going to pause it, and you can more or less see that it's starting to take shape. So now, as you can see, the actual analysis took literally about 1 minute and 16 seconds. And that is extremely impressive for a design as complicated and as organic in shape like this. No matter how good you are in design, you will never would have come up with that particular shape on your own. However, the algorithm generated this based on where to put the material based on these loading conditions. So I think the biggest impressive part to this as well is how now you can take this surface that has been generated, as you can see, and make this into a fully fledged component with mass and so forth. Well, you can do it in two folds. You can say generate the design. You can choose to make it a tessellated or faceted model, or you can choose to reconstruct. So now what reconstruct does, it basically uses the B-rep technology, where it basically recreates this geometry utilizing what we call subdivisional surface modeling that we have, which we always refer to as freestyle. So all that I have to do is just say regenerate, and this takes about a couple of seconds, and it generates the complete part. Now, as you can see, the reconstruction of the geometry is now complete. So this is a proper component that contains what you call subdivisional surface modeling. So now a user can go back at any time on this design and specify things like, you know what, I don't like having this cut out over here because maybe when I'm 3D printing this, to remove be it supporting material, it might be difficult. So I can make these changes. So I can say, how about I edit definition, the actual result, and based on this, I can state that, you know what, on here, on these, let me add another constraint, which is basically the minimum radius. So all that I'm doing now, I'm incorporating another design constraint, as you can see there. By just simply accepting that, I now can say, how about I quickly update these results? And you will see now that the results will look slightly different, adhering to what we've just stipulated now. So yet again, I'm just going to pause the recording just for about a minute so that we get to the result. So now that the analysis is complete, you can see that now the model is green in color, just to signify that the simulation has ended. All that I now need to do is update essentially how my finished product will look like. All that you have to do is update the B-rep that we've created, and as you can see with this one, we don't have the cutout in the middle there that could have made life tricky for us when we 3D printed or cast it or whatever the case is. Now I'm just going to update the B-rep. Now, as you can see, this is the updated model that we've just generated. So without wasting any time, you can easily take this and go and run a high fidelity structural analysis to just validate the structural integrity of this, just so that you make sure that it does indeed represent the strongest possible shape with the less material you can have. And of course you can take this and create rendered images if you like, or just put this on your report. And that is the power of generative design. And for this entire series, this is the first part video for generative design. I am going to be doing a follow-up onto this one. So for more videos like this, do not forget to subscribe, hit the notification button, and until next time, goodbye.